Alright, hi everyone, welcome back to the channel. This is the very first video of this dynamic programming series where we are going to be solving 16 CSES problems of dynamic programming. Alright, now in this video, we are going to be discussing all the prerequisites that you should have before you can actually start solving problems. And in this video, I am also going to help you develop the right mindset that you should have before approaching any DP problem. Alright, we are going to be discussing things like, what is the terminology used in every single DP problem? What is the difference between recursive DP, iterative DP, top-down DP, bottom-up DP? We're also going to be discussing things like how do you estimate time and space complexity when it comes to dynamic programming problems, right? Finally, we're going to also discuss where exactly can you use dynamic programming? Like what are the type of problems where DP is used widely? All right. So with that said, let's get started with this video. So first, let's get started by talking about a general mindset of solving certain type of problems. Okay. So let's suppose I give you a very big problem. Let's call it P. Okay. And somehow you don't know how to solve this very big problem, but you know how you can divide this problem P, which is a very big problem, into smaller subproblems and solve them. Okay. So let's suppose you end up dividing this problem P into three smaller subproblems, P1, P2, and P3. And you know that, it is easier to solve P1, P2, and P3 compared to solving P. Okay. So you're essentially doing this thing. You are given a big problem. You are dividing this big problem into smaller problems. Now let's suppose you come to P1 and you realize that P1 is also a very big problem to solve. So what you will do is you will further divide P1 into, let's suppose, smaller problems. Let's call them, A1, A2, A3, right? Then you come to P2 and you realize that, okay, P2 is also pretty big to solve. So you further divide it into smaller problems. Okay. And similar is the case for P3. You continue doing something like this until you hit a point where the problem is so small that you can trivially solve it. Let's suppose I tell you that, okay, there is an array given to you. Now again, this problem which I'm giving you can be solved in multiple ways, but with the mindset that we've just seen, let's try to solve this problem with that mindset. Let's suppose somebody asks you to print the sum of all elements. Okay. Let's say somebody says, give me the sum of all elements of this array. Now this array could be pretty huge. Obviously, it's pretty easy to solve this problem because you could just run a for loop from 0 to n-1 and sum up all the values. But let's suppose we, try to solve this problem with this mindset that we've just seen. This is a big problem. So we try to, break this problem into smaller chunks. Let's suppose I, say that first half of the array I will solve differently. Second half of the array I will solve differently. Okay. So you break the array into two parts. And then you realize that, okay, even these smaller halves are also pretty big. So you further divide them. Okay. Fine. You continue doing something like this until you hit a point where there is just one element left in the subarray that you're considering. Okay. Now clearly, if you have just one element left in the subarray, you already know the answer for that, right? If the value present was, let's suppose, AI, then the sum of this entire subarray is also going to be AI. Correct? Let's look at it in this example. Let's suppose the array was this. 1, 2, 3, and 4. Okay. Somehow, let's suppose you don't know how to, sum up all these values. So what you did was you divided this array into two parts. First was 1, 2. Second was 3, 4. Okay. Then you further divided the array into two parts. 1, 2. And this also 3, 4. Right. You know the answer for this problem, right? Because it is a trivial problem to solve. So you know that the sum of this part is just 1. Sum of this part is just 2. Now think about it. Can I use these answers of the smaller problems to find my answer for the bigger subproblem? For this problem, I can find my answer for 1, 2 by just summing up these two values, right? Whatever I've got from the lower subproblems. So clearly this gives me that, okay, the sum of this subarray is just 3. Okay. Now what I will do is I will look at this side. This is 3, this is 4. So I will sum them up and I will get that, okay, this is 7. Fine. Now look at the biggest subproblem that you were trying to solve. You can just sum up these two values and get your final answer. This gives you a 10. Right? So this is the, divide and conquer mindset that you need to develop. What you need to look at is this. Break a problem into smaller subproblems. Okay. You are given a very big problem. Try to break it down into smaller subproblems. And for these smaller subproblems that you are, actually breaking the problem down into, you also need to have a mechanism to actually, club them up together to find the answer for the bigger subproblem. If you look at this example, how were we finding the answer for 1, 2? We were saying that, okay, it is divided into two smaller subproblems. Whatever the answer that you get from here, let's call it X. Whatever the answer that you get from here, Y, just add them together to get my current answer, right? So this is a relation between the smaller subproblems that you have to find the answer for the bigger subproblem. Okay, so you need to think about this. Firstly, you need to think about breaking the problem into smaller subproblems. Next, you need to think about how can you get the answer from these smaller subproblems, develop a relation between them to find the answer for the bigger subproblem. Cool. Next, you need to think about what is that smallest subproblem for which you don't need to further divide it, for which you already know the answer, or it is trivial to calculate the answer for, right? This is known as the base case. Okay, where you don't have to further divide the problem. Cool. And eventually you are concerned about this thing. What is the biggest problem that you want to solve, right? In this example, in our array example, the biggest problem was this that we wanted to solve. Now let's talk about what exactly is dynamic programming, right? We've discussed how to divide a problem, but where does dynamic programming comes into the picture? Okay. So what you need to think about is that if you're dividing the problem into smaller subproblems, are there some repetitions that are happening? Okay. Can we be clever enough to identify these repetitions and not calculate them again and again? Okay. Let's try to see what I'm telling you. Let's suppose this was the biggest problem P that you were trying to solve. You divided it into 3 problems. Okay. Let's suppose P1 is further, divided into smaller subproblems. Let's call them A1, A2 and A3. Okay. And you realize that P2 is also further divided into 3 smaller subproblems, and one of them is A2. Let's look at it like this. Let's say this is A2, this is A4 and this is A5. Okay. Let's suppose P3 is further divided into smaller problems. One of them is A1, one of them is A4 and the other one is A5. Now understand it like this. These smaller subproblems that you're looking at, A1, A2, A3, all of these things, they would be further subdivided. Okay. They would be further divided into smaller problems. So think about it like this. Let's suppose you somehow got the answer for A1. You calculated the answer for A1 and you somehow know the answer for A1. Okay. Now look at this entire tree and see, is A1 being calculated again anywhere else? Yes, A1 is being calculated again here. So now think about it. You did some work to find out the answer for A1 and this A1 is being calculated again at some other place. Would you want to calculate this A1 again? The answer is no. You would want to somehow store the answer for A1 somewhere and then use it every single time it is required. Got it? So this is the idea behind dynamic programming. So let's suppose you wanted to find P. So for finding P, what you did was you came here and you said that, okay, first of all, get me the answer for P1. For getting the answer for P1, you went and said, okay, get me the answer for A1, A2 and A3. Let's say you know the answer for A1, A2, A3. Okay. And somehow you store it somewhere. Okay. Let's say you know that the answer for A1 is this, the A2 is this, and A3 is this. Let's suppose you've calculated it and stored it somewhere. Okay. Now you come to P2. Look at P2. P2 says that, okay, I need the answer for A2, I need the answer for A4 and I need the answer for A5. Now look at this thing. Look at A2. We already know the answer for A2. So what we'll do is we'll not go down here. We'll just say that we already know the answer. So we will retrieve it in some order of 1 time complexity from some memory location that we might have stored it at. Okay. Next we look at A4. Is A4 calculated already? No. So in this case we will go down. Okay. If A4 is not calculated, we will go down and calculate the answer for A4. But once we have the answer for A4, we will also store it somewhere. Got it? Similarly, look at A5. You don't have the answer for A5, so you go down, calculate the answer for A5. Now, if you know the answer for A2, A4 and A5, you will be able to calculate P2. Cool. Now come to P3. Look at P3. P3 needs the answer for A1, A4 and A5. It has the answers for all of these problems because you have already calculated them, right? So in this case, we will not calculate them again. We will just return the answer directly. All right. So this is the main idea behind dynamic programming. And many people like to call it memoization. This is very similar to saying memorization, right? So you can remember it like that. Memoization, memorization. So let's do one thing. Let's try to solve one problem on this and let's see how this entire thing works out. Okay. So this is a very famous problem, Fibonacci numbers. So in this problem, you're asked to find out the nth Fibonacci number. Okay, you need to find out the nth Fibonacci number and n is obviously greater than or equal to 1 and let's suppose n is less than or equal to something like 10 to the power 5. Okay, this is the range for let's suppose n. So what is a Fibonacci number? A Fibonacci number is defined like this, that f of 1 is equal to 1, f of 2 is equal to 1, And going beyond that, like f of 3, f of 4, all of these are calculated using this formula. That f of n is equal to f of n minus 1 plus f of n minus 2. Okay. If you want to look at this, let's try to see here. Let's suppose you're trying to calculate f of 3. F of 3 is going to be simply f of 2 plus f of 1. Alright. Similarly, let's suppose you're trying to find out f of 5. F of 5 is simply going to be equal to f of 4 plus f of 3. Okay, using that same formula that we have, that has been written here. Alright. So we need to solve this problem, and let's try to think about this same problem with the divide and conquer and dynamic programming approach. Cool. So first of all, let's say we are trying to find out Fibonacci of 6. To find out Fibonacci of 6, you need Fibonacci of 5 and you need Fibonacci of 4. So can I divide this bigger problem into smaller subproblems, and I also have a relation between these smaller subproblems to get my answer for the bigger subproblem? Can I say this? Yes. Because this f of 6 is nothing but calculating f of 5 and f of 4 and then just adding them up. Right? So I have divided the problem into smaller subproblems, but I also have a relation to combine these smaller subproblems to get my answer for the bigger subproblem. Alright? Now let's look at f of 5. How do you get f of 5? F of 5 seems like a big problem again, right? So you further divide it into smaller problems. For this f of 3, you further divide it f of 2 and f of 1. Now look at this, problem statement. It was already given to us that f of 1 is equal to 1 and f of 2 is equal to 1. So these are trivial cases. We don't need to further divide them. Got it? So these are also known as base cases. So what we know is that after f of 3 is divided into f of 2 and f of 1, we don't have to further divide f of 2 and f of 1. Got it? Now similar is the case for the other half of the tree. Now let's try to think about the same problem again from the dynamic programming perspective. We have understood the divide and conquer technique here. Now let's see, are we having overlapping subproblems? Are there certain problems which are being calculated again and again? And the answer is yes. See, look at this f of 3. Once you have the answer for f of 3, look at this entire tree and see where exactly is f of 3 being calculated again, right? F of 3 is being calculated 3 times. Should you be calculating it 3 times, or should you be calculating it once and storing the answer somewhere? The answer is you should be calculating the answer once and storing it somewhere. Got it? Similarly, look at f of 4. Now, if you look at the tree below f of 4, it's a pretty big tree. Similar is the case here. It's a pretty big tree, right? So as the number increases, the size of the tree below it is also going to increase. And in that case, it is always going to be very, very beneficial for us to actually store the answer. See here, let's suppose you got the answer for f of 4 and you stored it somewhere. Then when the next time you will come to f of 4, you will not calculate it again. You will only use that answer. So you will not be going down. You will directly be, saying that, okay, I know the answer for this f of 4. Got it? So this is the idea behind divide and conquer combined with dynamic programming. All right. Now you might say that, okay, Priyansh, you've told us that fine, we are going to be storing the answer somewhere and we are going to be retrieving it whenever it is needed, right? So how does that work out, right? So let's talk about that. See, let's suppose I tell you that, first of all, you must understand that all of these are subproblems. Okay, all of these are subproblems that you're trying to solve. For all these subproblems, you also now decided that, okay, a lot of these subproblems are overlapping. We are having to calculate them again and again. So do one thing, just store the answer for a subproblem somewhere and retrieve it whenever it is needed. Okay, but how do you essentially store things in memory? You can either store them in an array or maybe in a map or, like a set maybe. A set might not work because what you need is something like this. You need a key value pair. This key is going to determine that, okay, this is the subproblem and it is going to have a value which is going to be the answer. Okay, so this is the answer, this is the subproblem. So a very obvious thing to do is that you can, make use of a map. You can say that I will define every single subproblem by a unique key, and for that unique key, I will be having a value, right? This is one way to do it. A lot of people also prefer using an array, right? Why is an array preferred? Because obviously a map is pretty complex. It doesn't always have an order of 1 time complexity. In the worst case, it can go for an order of n time complexity. And if you're using a normal map, a tree map, in that case also the retrieval and the addition inside that map takes order of log n time. So preferably it is said that if you can somehow have this key as an index of an array, then both retrieval and updation would take just order of 1 time. Cool. So if you look at this subproblem, is there anything which uniquely determines every single subproblem here? And I would say it is this number 6, 5, 4, 3, 2. All of these things. These are unique numbers, right? F of 3 is going to be different from f of 2 because 3 is not equal to 2. Okay, so I have a unique key to determine every single subproblem here. Can I say that, okay, these keys can also act as indices of an array, right? I can simply just make an array and say this. Skipping, let's suppose the 0th index, we're not concerned about it. We're not concerned about this one. Let's look at 1, 2, 3, 4, 5, and 6. Can I say I can construct an array and I can store the values in that array, and whenever it is needed, I can just retrieve them. Yes, got it? So essentially for this problem, it is pretty cool that we can use an array, right? But for certain problems, you might realize that these unique keys that you're talking about, they might not always be integers. Okay, when you have integers, it is easy to use an array. But when these are not integers, it could be a string. In that case, a map would be preferred. Okay, so you must always understand that a map is like a superset here. You can always use a map, but sometimes it is better to use an array because that gives us an optimization in retrieval and updation. Got it? So let's see how can we, make use of an array and solve this problem. So firstly, if you're having this array, there are two operations that you're really concerned about. First is to check if this subproblem has been solved before. Okay, this is one thing that you need to care about. And second thing is to update / retrieve the value. Okay, see, in this array, you first of all need to check whether this value has been even calculated before or not. Because if you come to this f of 3 for the first time, you know for a fact that it hasn't been calculated before. So there has to be a mechanism which will determine that, okay, this value hasn't been calculated before. Okay, how do we do that? Understand it like this. See, all the values of the Fibonacci number can go from 1 to something like very big number. Okay, like f of x can go to, let's suppose, 10 to the power 18. Okay, we know for a fact that all of these numbers are going to be positive. All of these numbers are from 1 to as high as possible. So what we can do is that we can store some default value in all of these places, which will determine that, okay, this value hasn't been calculated before. Let's suppose I put a -10 at every place. Okay, let's suppose I put a -10. This -10 can uniquely tell me that, okay, this value hasn't been calculated before, because obviously the Fibonacci number can never be -10. So in order to check if this value has been calculated before or not, I can simply put a -10 at every single place. This -10 is known as a default value. Okay, this default value is going to be different for every single problem. A lot of people use -1 as a default value because in most cases the answers are positive, right? But in the case where answer can also be negative, you cannot use a -1 as a default value. You will have to think of a different default value, okay, which could be outside the range of your answers. Got it? Now this thing is done. In order to check if this subproblem has been solved before or not, we can just simply say, is -10 present at that index or not? If yes, we know we have to solve it, right? Once we have solved it, what we will do is we will just simply update the answer at that value. For 1 and 2, we already know the answers. So let's put a 1 and 1. Okay. When we get the answer for f of 3, we will just update it to this 2 because f of 3 is going to be 2. Now every single time when you come to this f of 3, you will just simply check in this array. Do you have a -10 present at that index? No, this means that the value has already been calculated. If it has already been calculated, just return that value. Got it? Cool. So this is how it's going to, proceed. So if you were to look at it, let's try to understand it like this. F of 2 and f of 1, you already know. Once you have the answer for f of 3, you update it to as 2, right? Then if you look at f of 4, for f of 4, you need f of 3 and f of 2. F of 3, once you have the answer for f of 3 and once you have the answer for f of 2, you can get the answer for f of 4 by adding them up. Okay, so f of 4 comes out to be 3. Okay, similarly f of 5, f of 5 you can calculate now because you know the answer for f of 4 and f of 3. Look at this f of 3. Are you going to calculate it again? No, you're just simply going to use its answer. So just add them up together and get the answer for f of 5. So f of 5 becomes 5. Okay, and similarly you can get f of 6 by looking at f of 5 and f of 4. Again, you will not be calculating f of 4 again. You will not go down because you already have the answer for f of 4. Okay, so you'll just add them up and you'll get your answer for f of 6. Got it? So this is how it entirely works. Okay, What did you learn from this? There are two things that you need to care about. How do you check if this subproblem has been solved before or not? Okay, simple. You can use some default value for that. The second thing is, how do you retrieve that value? Okay, and for that, like, you know, if it is an array, you can just directly access the index. If it is a map, you can access that key. So let's look at these three codes. First of all, let's look at the brute force code. Okay, see here, we were trying to find out f of n, right, which is the nth Fibonacci number. So what we'll do is we'll just call f of n, and then inside this f of n, all the work is happening. First is the base case, where if n is less than or equal to 2, you know that f of n is going to be 1. So you return 1. Otherwise, if you know that n is greater than or equal to 3, then in that case, you have to first of all find out f of n minus 1, find out f of n minus 2, add these values and return it. Okay, so this essentially is divide and conquer. This is divide and conquer in the true sense. Okay, but now how do we, use DP here? How do we use dynamic programming, or how do we make use of the fact that there are overlapping subproblems? We are calculating a single problem again and again. This you can look at in terms of this DP thing. See, what are we doing? First of all, we are saying that, okay, if it is a base case, just return 1. We are not really concerned about anything. Otherwise, what you need to do is, you first of all need to check if this value has been calculated before or not. So here in my case, I have used my default value as minus 1. Remember, this concept is very important. You are not always going to use minus 1. In this case, I am able to use minus 1 because all the Fibonacci numbers are going to be positive. Got it? So this minus 1 just tells me that this particular problem has not been solved before. Got it? So in that case, I will just, if this problem has been solved before, in that case, dp of n will not be equal to minus 1. So I will just return dp of n. See here, I am not calculating the answer again. The calculation actually is happening here, right? If dp of n is equal to minus 1, this means that this is the very first time that you're coming to this problem. So you need to solve it. How do you solve it? You just get the answer and then you return it. Got it? This is the brute force code. This is the recursive code, recursive DP code. Got it? Now let's try to see how does this work out in the iterative sense. Before I, actually start discussing the code, let me explain it to you. Because essentially there is no difference between recursive iterative. It is all about the mindset. So see here, you wanted to find out f of 6. You know that to find out f of 6, you need f of 5 and f of 4. To find out f of 5, you need f of 4 and f of 3. Right? So what does this show us? This shows us that in order to find out f of n, this f of n needs f of n minus 1 and f of n minus 2. And similarly, in order to find out this f of n minus 1, it further needs f of n minus 2 and f of n minus 3. This f of n minus 2, in order to calculate it, it further needs f of n minus 3 and f of n minus 4. So doesn't it show us this, that first of all, you need to calculate the answer for the smaller problems, and then you can calculate the answer for the bigger subproblems? Yes, this is how it works in the case of iterative. All you need to know is that which are the problems that need to be solved first and which are the problems which can be solved later on. So think about it like this. Can you solve f of 3 after f of 6? Can you do this? If you don't know the answer for f of 3, can you ever calculate the answer for f of 6? No, because f of 6 is indirectly dependent on f of 3. So f of 3 must be calculated before f of 6. Got it? So if we know the answer for f of 1 and if we know the answer for f of 2, we can directly get the answer for f of 3. If we know these two answers, we can directly get the answer for f of 4 and so on. Right? So what this means is that the smaller values of this key that we're talking about, they should be evaluated before the bigger values. So what we can do is that we can start by evaluating this, and so on. Right? And this is how the iterative code looks like. See, first of all, we say that dp of 1 is equal to 1, dp of 2 is equal to 1. And then after that, we just know that in order to calculate dp of I need dp of I minus 1 and dp of I minus 2. And both of these values would have been calculated because I'm iterating like that. Got it? So dp of I is equal to dp of I minus 1 plus dp of I minus 2. Now just compare these three codes. First of all, this is very, this is not optimal. If you run this code for, something like, let's suppose n is equal to 30. If you run all these three codes for n is equal to 30, this is going to perform very, very bad, this brute force code. But both these recursive and iterative codes, they're going to perform equally well. Got it? So yeah, in case of iterative, you must understand that there is a little more thinking, but this is no rocket science, okay? Now let's talk about, how do you actually solve a DP problem? What is the mindset that you should have when you're solving a DP problem. Although you already know it right now, but now we'll be talking about certain terminologies. Okay. So the very first thing is that you need to think about a sub-problem that you're solving. Okay. You're given a problem, you're given a big problem in the problem statement of any CP problem. You have to divide it into smaller problems, and all these smaller problems are going to be called subproblems. Okay. So you need to think about a good subproblem. That is very important. In our case, what did we do? In our case, we say that, we said something like this: DP of n is equal to nth Fibonacci number. We said something like this in the Fibonacci problem. So here, determining this sub-problem was very easy because it was already written in the formula that f of n is equal to f of n minus 1 plus f of n minus 2. So you knew for a fact that this I can make as a sub-problem. F of n becomes a sub-problem. Now f of n, dp of n, both of them are the same things. Okay. When you are thinking about the sub-problem, what is important? The most important thing is the parameter. The key which is uniquely going to determine your subproblem. In our case, what is it? It is this n. We know for a fact that dp of 1 is different from dp of 5, let's say. Why? Because these two values, 1 and 5, are different. So you need to think about this parameter. What is that parameter which uniquely determines this state? Okay. Because ultimately it is nothing but, like obviously I'm saying state. So this subproblem is also called a state. Going forward, I will always be calling a subproblem as a state. Got it? So essentially what happens is that you have a lot of states. Okay. When you're solving a problem, all of these states are there. Some might be big, some might be small, but there has to be a mechanism to uniquely determine, okay, that this state is different from this state. This is very important, that this thing is not the same as this thing. There has to be a unique method to determine it. And that is, determined by the parameters that you use in the state, right? Next, you need to think about, how you can break this bigger problem into smaller problems. Again, in the Fibonacci problem, it was already obvious to us, right? That f of n is equal to f of n minus 1 plus f of n minus 2. So everything was given to us. But in most of the DP problems, this relation will not be given to you. You will have to think about the state on your own. You will have to think about the smaller subproblems on your own, and also the relation on your own. Okay, so that is what we're going to discuss in this entire series. Fine. Now, it is also about, determining what is the relation between these subproblems. How can you calculate the answer for bigger subproblem with the help of these smaller subproblems? So that is known as a relation, and this is also known as a transition. Got it? Now, before we, go further, it is also very, very important that when you're, writing that this is the subproblem, you must define it. Okay. See, here I've defined it like this, right? dp of n is equal to nth Fibonacci number. This is very, very important. This statement, if you don't write in a DP problem, nobody is going to understand. In fact, you yourself are not going to understand that what is your DP state meaning. Got it? So this is very important. Next, you need to think about this thing. What is that smallest subproblem which you don't need to solve further? This is known as the base case. And finally, what is the biggest problem that you were trying to solve initially? That is known as the final subproblem. Okay. So going forward, all I would require you is to just understand this thing. This one method of how to solve a DP problem, I am going to be using this same method to solve all the 16 DP problems which are coming up. Okay. But I want you to use this just one method, not any other method like saying, I would first use a recursive method, then I would use tabulation. No, we are not going to do all of that stuff. Got it? And trust me, after these 16 problems, you will realize that with this method, there is no problem that cannot be solved. Okay. Cool. Now, you must have also seen that when I showed you the code for this Fibonacci problem, I showed you two codes. One was recursive and one was iterative. So this recursive code is also known as top down, while the iterative code is also known as bottom up. Let's see why this is the case. See, when you're trying to find out Fibonacci of 6, you start from here. You say that, okay, in order to find out Fibonacci of 6, I need Fibonacci of 5 and Fibonacci of 4. So you're going from top to down, right? This is known as top down approach. And when you're doing an iterative approach, what are you doing? You're first of all getting f of 1, then you're getting f of 2, then you're getting f of 3, and so on, and then you're getting f of 6. So if you were to compare it with this tree, this approach, this iterative approach looks like a bottom up approach, where you're calculating the answers for the bottom problems first, and then you're going up. Now here I'm not going to stress upon these concepts a lot, top down, bottom up, recursive, iterative, because after these entire 16 problems, after this playlist, you're not going to care about these concepts because these are not important. What is important is that same mindset that I've showed you. Okay. Now, one thing that you must understand in case of recursive code is that you require a stack space. Okay. Look at this code. How does this code work? This one. It requires a stack space. In order to get f of 6, you need to find out f of 5 and f of 4. So f of 6 is saved. You first of all find out f of 5 and f of 4. F of 5 is saved. To find out f of 5, you need f of 4 and f of 3. So essentially the stack builds up. So there is a stack space which is handled, right? And which also accounts for a higher runtime. Okay. So recursive codes are generally slower. So it requires a stack space and it is generally slower. Okay. Now, one thing that you must understand here is that when you're coding a recursive solution, the flow is not really important. Okay. Like you just started from f of n and then you just expected the recursive code to give you the answers, right? There was no thinking involved as such. But when you looked at the iterative code, there was thinking involved. You had to care about which states or which subproblems need to be solved first. Okay. So this is the main difference between recursive and iterative code. And essentially after this playlist, again, I'm telling you, you're not going to care about these concepts. Fine. Now let's talk about one more thing. What is the time and space complexity of DP problems? This is also very important because ultimately you're just trying to optimize the time, right? Time and as well as the space. So let's think about it like this. Let's say you have these states, okay? You have S1, you have S2, you have S3, you have S4, okay? In order to find out S1, you need the answer for S2 and let's suppose S3. So what we'll do is that we'll assume that S2 has been calculated already. S2 and S3, you already know the answers for these subproblems. If you know the answers for these smaller subproblems, you can find the answer for S1 through a relation. Let's suppose that relation would have been something like S1 is equal to 2 times S2 plus 3 times S3. Okay, let's suppose this is the relation. If you look at this relation, how much time are you going to take to evaluate this relation? This is just order 1. Because you're just having, like a single relation. You just have to add 2 integers and that's going to give you your answer. Correct? So this is order 1. Let's suppose you would have had something like this. That in order to calculate S of n, you have a relation as something like a of S1 plus b times S2 plus c times S3 and so on up till, let's suppose, x times Sn minus 1. If you had to evaluate this expression, how much time would this take? This would take order of n time. Because you're adding up n values, right? So you will have to first of all get all these values and then add them up. Okay. So whenever we are trying to find out the time complexity of a DP problem, what we'll do is that we'll assume that these answers are already calculated. Because if these haven't been calculated, how are you even going to get S of n, right? So we'll assume that all these answers are already present. Now we'll just say that for a given state, how much time is required to calculate its answer from the known states, right? So this is the LHS, this is the RHS. When getting the time complexity, we'll say that the RHS, all the terms in the RHS are already present, okay? Because see, what I'm doing here is this. I'm saying how much time is required to calculate S1, how much time is required to calculate S2, how much time is required to calculate S3. Okay? I will, find out this time differently, this time differently, this time differently. But if S4 requires S1, S2 and S3, I am not going to say that S4 also requires this much time again. S4 doesn't require it. Because why? Because we already have the answers for S1, S2, S3, right? So in order to get S4, we are just concerned about how much time is required to evaluate the expression. Okay. So essentially the time complexity just reduces down to something like this. Number of states, how many subproblems do you have? And what is the average time required to calculate a state? Okay, this is the main time complexity. Okay, if we were to look at the Fibonacci problem, okay, what is the number of states in the Fibonacci problem? See, we had f of 1, we had f of 2, and so on up till f of n, right? So there are n states. How much time is required to evaluate one state? Just order 1, because f of n depends on f of n minus 1 and f of n minus 2. Both these answers, if they're present, the answer for f of n can be retrieved in order of 1. So number of states times the average time to calculate one state. The average time is the same here for every single state. Every single state is going to require 2 integers to be added up. So that will become order of 1. So overall time complexity for the Fibonacci problem is just order of n. Okay. Now see, this is one formula that I've already told you, just multiply the number of states with the average time to calculate every single state, this might not be true in every single sense. So let's take an example and see where this formula might not fit and where you might have to come up with a different formula, okay, to get the time complexity. So let's suppose f of 1 could have been evaluated in order of n time. F of 2 could have been evaluated in, let's suppose, n by 2 time. Okay, and so on, and f of n would have been evaluated in, let's suppose, order of n by n time. In this case, if you add up all these times, it will not come out to be n square. Okay, it will not come out to be n square, it will actually come out to be n log n. So when you have a time complexity, when you have a state which is evaluated like this, then this formula might not work. That just multiplying by the number of states by the average transition time. Okay, so this formula, when you're using, use it with a pinch of salt. In certain problems, you might be able to come up with a better bound if you don't use this formula, but you use this formula, total transition time. Okay, so total transition time is nothing but saying something like this. Let's suppose there are n states. So for all the n states, you're going to just add up transition time for state I. Okay, see, both of these things are essentially the same only. When the average transition time for every single state is kind of the same, then this formula also works pretty well. But in a lot of problems, not in a lot of problems, but in some problems, you might have this condition that a single state is taking a very long time, but some other states are taking very less time. So this average is not going to come out very well. Okay, so in this case, you might have to do something like this. Now, finally, let's also talk about where exactly is DP used. What are the type of problems where DP is widely used? One of the things is, where you have to find out the number of ways to do a particular task. There DP is used widely. Secondly, when you have to find out the minimum or the maximum answer in a certain problem. For example, when we were looking at the tree, we could have had the problem as, what is the shortest path from this node to some other node, right? In, let's suppose, the tree. That could be done with DP as well, if you have like multiple ways to get to that same point. Okay. Similarly, when you have to check for possibility, when you are given a problem, you have to try out all the possible ways and say whether one of them is the correct way or not. There also DP is widely used. Okay. And how I like to view DP is that by saying that it is nothing but optimized brute force. Although it is not brute force exactly, it is divide and conquer, but I like to treat it like this, that it is nothing but optimized brute force. Because generally, I tend to think about problems in a brute force manner, and DP acts as an optimization on them. Okay. And finally, DP is nothing but all about identifying the overlapping subproblems. Got it? So yeah, that was it, guys, for this video. I hope you all learned a lot of stuff from this video. Starting from the next one, we'll be actually solving problems. So before you go on to these next videos, I would recommend you to first of all watch this video, because this video is all about developing the mindset. And then after that, it is just about applying that mindset. Got it? So yeah, that was it for this video. Just feel free to, subscribe to this channel and press the bell icon to not miss any future updates on the series.